Okay, the last time we left off, we finished. Oh wait, so that means we need a quiz. So here's the quiz. I know you were hoping I totally forgot. 3, 1, 2, 1. So just so you know, if you're that electric fuel pump, in addition to, there's at least 4 times you're going to need to have it on. One of them is takeoff, one of them is landing, another one is you're going to check it before takeoff when you're doing and run that fuel pump on and make sure it moves so you know the fuel prep pump is working correctly. If there's a problem, it doesn't work correctly, you don't know if it's the engine-driven fuel pump or not, so you're going to turn on that electric pump. Having trouble in flight or of any kind, you're going to turn that fuel pump on. Number 2, you're going to check it before takeoff to make sure it's working. 3, you're going to use it during takeoff, and 4, you're going to use it during landing. Anybody have any questions about that? Number 3, during the pre-flight inspection of an airplane, what do you think is our pilot looking for when draining fuel from the bottom of the fuel tanks? Oh, darn, I left it up here. Sediment and water. But I want you to go in your notes, and I want you to add a third one. I kind of talked about it earlier than that when I talked about wrong fuel, but the third one, I want you to put its color of the gasoline. If you put jet fuel in it, in a little tiny bit, it changes it to clear. What you're looking for is blue. 100 octane low lead has a very light blue dye. It's actually dyed blue. It's not naturally blue. It's a very light blue. So that third thing you're going to be looking for is correct fuel color. Because if a little bit of jet fuel gets in there, it destroys the dye and it looks clear. You're going to start thinking something's wrong. It needs to be a very light blue. And it'll make a lot more sense when you start taking flying lessons. You start drinking gas out of fuel tanks and start drinking it. Inhaling it. Smelling it by accident. And just so you know, there's a downside to aviation gasoline. 100 octane low lead has 2 milliliters or 2 cubic centimeters of tetraethyl lead in it. So you can get you are being lead poisoned at an airport that has gasoline-powered flying machines at it, because that lead is going into the atmosphere after it gets burned. And if that gasoline gets on your skin, some of it will soak into your skin. Anybody ever heard of the Center for Disease Control, the CDC? Nobody's ever heard of that? How about the FDA, the Food and Drug Administration? Okay, between those 2 organizations, you know what they have as the maximum allowable amount of lead poisoning for humans? It's none. The maximum allowable amount is 0. So when you let aviation gasoline get on your skin or you inhale it, by sticking your head over a fuel tank and smelling it, or you smell airplane exhaust that's burning aviation gasoline, you're getting more lead into your body than the federal government thinks is a good idea. Just so you know. There are plans, the FAA is working on getting the lead out of gasoline, out of 100 octane, but it's going to be a few years. So last we left off was refueling. And so we're going to go to exhaust. We're going to say the exhaust contains just a couple of things. Exhaust ducts. On cars, you probably call them exhaust pipes. We're also going to look at some heat exchangers and to provide heat for the cabin, and heat exchangers also provide heat for the carburetor heat. I'd like you to notice that nowhere on here, on this list here, does it say noise reduction mufflers. All airplane and helicopter engines that have run on gasoline or diesel have straight pipes. There is no muffler to slow it down. There is no catalytic converter to reduce emissions. Aviation is the only thing exempt from the non-leaded fuel laws of the late 1970s or early 1980s. I can't remember when they came out, when the United States switched to unleaded gasoline, but the aviation got an exemption. There's no mufflers on little airplanes. What you see is a heat exchanger. So here's a picture of a heat exchanger. And I'm going to see if I can draw with my gizmo here. Hopefully I can do that. Whoops. I think I can. All right. So if this is a 4-cylinder engine, the exhaust is going to come out of all 4 cylinders, and that's this example here of a heat exchanger. This is bolted underneath the engine, and the exhaust has come out of each of the 4 cylinders. And that exhaust pipe, the exhaust comes together on the inside, and that doesn't show it very well. But those 4 exhaust pipes are all welded together, and then they go overboard. They go overboard or off of the aircraft or out of the aircraft. What this doesn't show very well, and I'm going to use a different color, I think. We'll use another color, is outside air can come in here and go around the exhaust pipes and then down and then out. It doesn't show it, but there's a hole on the other end, and this air can go out, and now this air is hot. And you can either run it to the cabin, and you can also run it to the carburetor. Oops, can't spell carburetor. But I want to make sure you understand that this is not exhaust gases. This is fresh outside air that's touching the exhaust pipes. So when you pull the knob inside of a little airplane and it says cabin heat, the air is going around the exhaust pipes. But if the exhaust pipes aren't leaking, you might get a little bit of a hint of a smell of a hot exhaust pipe, but you're not going to breathe exhaust fumes. The problem becomes when that exhaust pipe cracks and some of the exhaust gases leak into this nice fresh air. And it may be a small enough crack that you don't notice the smell. And we're going to talk about carbon monoxide poisoning, and that's the big issue here. Is not that you're going to get carbon dioxide. Carbon monoxide is a gas that when it gets into your bloodstream, it attaches to your red blood cells. And it'll stay in your body for a long time. And we'll talk about later when we get to physiology what you need to do about it. It's things like turn off the cabin heat. Make you lose consciousness. If your IQ's 200 and you drop down to 100, I guess you're still okay, but I don't know anybody whose IQ is 200. The propeller. I'm trying to think of this little tiny airplane you can fly as a private pilot that doesn't have a propeller. There's very, very, very few of them. There's an experimental airplane or two that has a jet engine. There's some military surplus airplanes you can fly as a private pilot, but the likelihood of you flying them for training is pretty much zero, so that means you're going to fly an aircraft with a reciprocating engine, and it's going to have a propeller. It is a device that takes the rotating energy from the engine and converts it to thrust. I mentioned in a previous lecture that the gasoline in a gas engine, or the diesel, it has chemical. So that engine is to convert that energy into thrust so we can go forward or to climb. There are two basic types of propellers we looked in class. A fixed pitch propeller means the blades don't change how much air they grab. It's like being stuck in a single gear. It's like being stuck in third gear. If you've got a 4-speed automobile, it's like being stuck in third gear. So it means it takes you a little while to get off the ground, but you'll get off the ground and you'll climb. But you won't go as fast as you could if you could go to a higher gear. But the nice thing about fixed pitch propellers is they are simple because there's no moving parts. You guys are writing this down. Fixed pitch propellers are simple because there's no moving parts. And number two, they're very lightweight. And and since they're simple and there's no moving parts, guess what? It's almost impossible for them to fail. The thing you're going to look for on a pre-flight inspection is nicks in the leading edge. And if the nick is, generally speaking, if it's bigger than 1/8 of an inch, you're going to not fly that day. Variable pitch propellers are like having gears in a car, but instead of just having first gear, second gear, third gear, fourth gear, it's an infinite number of gears. All the way to 1 and 2. It makes it on a shorter runway. So if you took, say, for instance, let's say an 0360. An 0360 is made by Continental. It has 360 cubic inches of displacement. It puts out 180 horsepower if you run the engine line. Or you're stuck in third gear. So at first, that engine going to be able to spin around all, let's say the red line is 2,700 RPM. Is that engine going to be able to spin 2,700 RPM? No. If you had a clutch, you'd be slipping the clutch quite a bit. But still, third gear probably works really good for 100 miles an hour, but you're going to take off at, say, 70 miles an hour. So that third gear still isn't even that good at 70 miles an hour. So the engine will not get up to red line. So even on takeoff, you won't get that 180 horsepower. So it'll take longer to get down the runway. But if I had a variable pitch propeller and I could, instead of being stuck in third gear, down when I'm at 0 miles an hour, half gear, and it moves to 1 first and second, and I get off the ground in second gear, and it keeps going, I can actually get all that horsepower out of it I want. I can actually have the engine at redline RPM and get all 180 horsepower out of it. And then when I level off, the blade will go to a higher and higher pitch and grab more air, and I can have fourth gear. Heck, I can even have fifth and sixth gear. So if I wanted to continue to use that 180 horsepower, I could. Usually you'll pull the throttle back about 5 or 10 or 20%, so the engine doesn't wear out too soon. But you're always going to be able to have the best gear. But it costs more, and complex is higher. And that's the blue lever. If you're inside a bit of an airplane, there's usually 4 levers for the aircraft. Let's see. So if here's an instrument panel, there's usually 4 levers. If it has a variable pitch. So one of them here is going to be the carb heat, and it's usually black. And then you're going to have the one that you wiggle the most, that's going to be the throttle. But if you have a variable pitch propeller, the prop lever is going to be just to the right of the throttle, and it's usually blue, like the ink I'm using. If you're on a training airplane, isn't going to be there. So then you only got 3 levers. Propellers are usually made out of aluminum. You don't have to write this down, but the next most likely propeller you'll find on a little airplane is made out of laminated wood. Laminated just means layers of wood glued together. The next, that's usually on older airplanes. There are some composite propellers, that is, they're made out of fiberglass or Kevlar or carbon fiber, but that's less popular. I'd say 99% or more of the airplanes out there that are little airplanes have propeller blades that are made out of aluminum. So I've talked about out in the lab about propeller hazards. Chopping your head with the propeller is bad. So the hazard of a propeller is if the engine rotates because gasoline burns inside of one of the cylinders and it spins that propeller around at 50 or 100 miles an hour. Remember, it's like taking a aluminum base, filling it up with aluminum, and then shaving it so it's kind of sharp and getting hit in the head by somebody. So to prevent this, we take several precautions. So let's list the precautions. 1, pilots always shut the engine down with the mixture control. That keeps the fuel out of the engine. Number 2, if you have to rotate the propeller, you try to rotate it backwards. Why do we rotate propellers backwards? The ignition and the engine is spinning backwards. What's another precaution that we take with propeller blades? We always head out of the plane of rotation, so no matter if we, of those other things that fail, and it spins, our head isn't there. So those are the 3 biggest things that you're going to do. So there's a nice picture of a propeller. You'll notice that close to the propeller hub where it's bolted to the engine, on this slide the hub is there far on the left. You can see the black holes, that's where the bolts would hold it onto the engine. You notice close to there, the propeller is thick. And each portion of the propeller has a slightly different airfoil. And you'll notice the closer and closer you get to the blade tip, the angle of attack is less. Angle of attack is how much air it scoops out. You notice way out on the far right of here, it's at less of an angle. That's because it'll get the same amount of lift, or thrust in this case, but it's spinning faster. When we get to aerodynamics and we start talking about wings, there's several different things you can do to get more lift, or in this case it's thrust. But the propeller is just a spinning airfoil. So one way to get more lift is to have it at a higher angle, like on this case closer to the hub. Towards the left, the blade is at a higher angle. But that's because right there near the hub, it's spinning slow. Its speed or going around the engine is slow. But out of that blade tip, it might be going 300 miles an hour, so it's getting a lot of lift. It doesn't need to have a high angle of attack. It has a lower angle of attack. All right, now your personal favorite and mine. And when I say that, you don't yet know that it's your personal favorite. Aircraft electricity. Well, I did have a very, very, very nice handout. Oh, wait, there it is. So I'm going to pass out a very generic electrical. So just for fun while I'm passing this stuff out, how many people in here have ever done troubleshooting on an electrical system of any kind? One person. What kind was it, Jared? It was a circuit in your house? So you stuck a voltmeter in there to see if it was had power? Okay. Jonathan. Yeah, you were trying to troubleshoot the ignition system of the lawnmower. Okay, so some of you are not completely ignorant, but most of you are, and don't feel bad. When I say ignorant, that just means there are things you don't know. It doesn't mean that you're a bad person or your value as a human is less than others. So there are a boatload of things in an electrical system, so I'm going to let you write down this list, and then we're going to start looking at them in the diagram. Is the list never ending? Okay, in this case, that's as many as I could conveniently stick on one slide. So as far as testing purposes, we're only going to talk about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different components. Oh, awesome, only 10. What I found while you're writing that down, what I've found is that most people don't like electricity. And I found of those people that don't like electricity, it's because they don't understand it. So my attempt here is to not get you to enjoy electricity, but my attempt certainly is So this is how bad it was for me. I took 2 years of electronics in high school. One of the jobs it was a job was I was an electrician. If electrical things side. Nearly not even a tenth. We're just talking about electricity that pilots need to know. So here's that diagram. So I recommend you turn yours sideways, and we're going to label it. And then on your notes, I suggest you take notes about what that thing does. So the first thing right up here, we're going to call this the bus bar. Notice that everything on the schematic is connected to the bus bar. So we're going to come down to this little gizmo here on the bottom left. We're going to put a negative sign and a positive sign, and we're going to call this the battery. So these are actual schematic symbols for most of these components are actual schematic symbols, and that's what a battery looks like, a long, a short, a long, and a short. And then usually batteries are labeled. On most little tiny training airplanes, they're 12-volt systems, but some of them are 28-volt systems or 24-volt systems, and we'll talk about that probably not today because we've only got 20 minutes till class. I've got a switch up here. We're going to call this the master switch. I've left out some details. You know what? Let's don't call this the master switch. We're just going to call this a switch. And you'll notice I've got another switch over here and another switch over here, but I'm not going to label them. If you have any questions while I'm going along, don't hesitate to ask me. So let's just say for fun that we close this switch. The way I drew the switch was this bar was open, or this handle was open. That's in the off position, but the way I draw it right now, that's the on position. The positive side of the battery be connected to the bus bar. We're also going to label this thing down here, and this thing down here is called a ground. A ground is really just a wire that's connected to the fuselage or the wing or other metal part of the aircraft. That's now connected to all the other metal parts of the aircraft. If you've ever worked on a car, you'll notice that the negative side of the battery is bolted to the chassis of the automobile. And if you looked close enough, you'd end up finding a wire that goes from the chassis or the body of the car to the engine, because the engine is usually on rubber mounts, and so it's insulated and isn't touching the car. That way, all the metal parts on the car are touching each other. Same thing with airplanes. The negative side of the battery is connected to the ground. And you'll notice there's these other ground symbols down here. What that means is they are all connected to the metal of the airplane. So I'm going to draw, and I suggest you do it, I'm just going to draw a line connecting all of these grounds, because now effectively they are all touching each other. And more importantly, they are all touching the negative side of the battery. You notice the negative side of the battery is always touching the ground. That means this point right here is touching the negative side of the battery. And this point right here next to this light bulb is actually touching the negative side of the battery. And this side of this component is touching the negative side of the battery. And this side of this component is also touching the negative side of the battery. And there's no switches in here. And this is the way it is in cars and the vast, vast majority of electrical circuits, is that these components in here are all touching the negative side of the battery. Now, as soon as we turn on the master switch, if we turn on this electrical master switch, that connects the positive side to the bus bar, that now means that things on the airplane can work. And when you do that in your car, it's when you turn that key to the on position, but you don't turn it all the way to start. When you turn that key to on, things start happening, right? Lights come on, the radio comes on, stuff like that. It's because what you've done is, there's other things that ignition switch in your car does, but one of the things it does is it connects the positive side of the battery to a bus bar. And now in cars, they typically have fuses. In airplanes, we usually have circuit breakers. That's what this item is in here with a little T on it. And this is a circuit breaker. So in this case, there are two of them on this diagram. A circuit breaker is just a fuse in that it's designed to open the circuit to prevent the wires from getting too hot. So I'm going to say that again because I know you want to write that down. He said jokingly. I'm not joking. A circuit breaker will open the circuit and stop electrons from moving if too many electrons go through the circuit. So in a car, it's usually a fuse, and now you got to have extra fuses. But in airplanes, there are usually circuit breakers that'll actually pop out, and that way the pilot can just push it back in if they need to. That way you don't have to have a bunch of fuses floating around. Brian, question? You bet. Yeah, a circuit breaker will open the circuit and stop electrons from moving if too many electrons are going through the wire. It'll stop it. Literally, it is a switch that is activated when too much electricity goes through it. The switch will open, and you don't have to move it. It does it automatically. Now, people get confused about circuit breakers and fuses. You got to understand, circuit breakers and fuses are not there to protect the component. The size of that circuit breaker is based on how big are the wires, how much electricity can go through the wires. That's what the circuit breaker is doing. Think about a house and the circuit breakers. Has anybody ever looked at the circuit breaker box of a house or an apartment? Okay, those things pop. A house from 1942. But something, right? Inside the house, turn it off, and then go out to the circuit breaker box and move the fuse of the circuit breaker back to the ON position. ON is a spelling for a word called on. So the OFF position. That's the off position. Yeah, there's actually a joke about who wrote up a radio that said, this radio does not work in the OFF position. I'm not making that up. I mean, it may be a story, but I didn't invent the story. In any case, think that circuit breaker in the side of your house is not there to keep from sending too much electricity into your stereo or your grow lights or whatever it is you have plugged into the basement from getting so hot that they cause a fire. About the fires, they're of a wooden frame most of the time. Most houses in the United States is made out of wood. What if the wire got so hot that the insulation melted and the copper wire got red hot and it caught the wood on inside the walls of your house? Would you be while you're sleeping while the house catches on fire? I think you would not be happy. So the size of the circuit breaker is dependent upon the size of the wire, and it's there to keep the wires from getting too hot. It does not save the component. It doesn't save your stereo, your grow lights, or on an aircraft, it doesn't save the radios or anything else that the circuit breaker is set up for. It's there to prevent electrical fires. It's there to keep the wires from getting too hot. Okay, so just for fun, we're going to follow these electrons. Electrons, you can write this down in your notes. Electrons go from negative to positive. Electrons travel from negative to positive. And you can think of a battery that's charged up, has too many negative electrons, on the negative side of the battery. You can also think of a charged battery where it says positive. Positive is where there are not enough electrons. When you charge up a battery effectively, and I'm oversimplifying it, but when you charge a battery, you effectively grab the electrons out of the positive side and stuff them around onto the negative side. So now there's too many electrons on the negative side, and we're going to say that if there's not enough electrons, it is positively charged. So all these negative electrons are going to try to go somewhere, somehow, through all of our stuff, through the bus bar, through the switch, and go to the positive side of the battery. So the flow of electrons is in this direction when the battery is getting discharged. So I'm going to write the word DES. That's not a short term for disrespect. That's a term for discharge. So when the battery is discharging, the electrons are going to leave the negative side of the battery, and they're going to try to go to the positive side because there's not enough electrons. If you haven't heard this before, opposites attract. Well, it certainly, I don't know if it works very well in personal relationships, but in electrical, that's exactly what happens. Electrons are attracted by wherever it's positively charged. Positively charged being a place where there's not electrons. So the electrons are going to try to get away from when there's too many electrons, and they're going to try to go where there's not enough. You're right there. If you don't get that, if you can't remember that, then it's going to be hard from here on in. Electrons are negatively charged. A charged battery has too many electrons on the negative side, and try to go where there are not enough electrons, or not enough electrons at places where it is positively charged. So when you turn on the electrical master switch, or in your car you turn on the key, since the negative side of the battery is already connected to ground and to everything else, all you're doing is connecting the positive side of the battery to the bus bar. So just for fun, you don't have to write this one down here, but let's just say this is my car radio. I left it turned on before, and I left the volume up. That means when I turn on the master switch, when I turn on the key, the bus bar is connected to the radio. So one side of the radio is connected to the positive side of the battery, and the other side of the radio, since everything that's grounded, is connected to the negative side of the radio. This side of the radio is negative, and now I have a place where electrons can go. Those electrons will leave the negative side of the battery. They will go through the chassis of the car, the metal of the car. They'll go through the ignition switch on your car, and they will go to the positive side of the battery. And when that happens, there's one less electron here, and there's one less place that wishes it had electrons. So now the battery has discharged a little tiny bit. And if you don't turn on the engine and you don't turn on the alternator or a generator, or you don't jump it, this battery is slowly going to discharge. And I'm just making up a number, but if you're in your car and you have the radio and a bunch of other stuff turned on, the ignition, a lot of other things are turned on using electricity, most cars, the battery will go dead in anywhere between 20 and 40 minutes, depending on how much stuff you got turned on. Or what if the light stays on in the top of the car on the inside? You come back 8 hours later, the battery's dead, because literally this electron goes through, and you don't have to write this one down, but it goes through that light bulb, because the switch on the door or whatever it is closed, and that battery discharges, and now again it's filled it up. And if it does that enough, if the next electron goes, and guess what happens? After a while, you end up with not enough places, not enough negative electrons, and not enough places where the electrons are attracted to, and the battery goes dead. This theory right here applies to AA batteries, and C batteries, and D batteries, and 9-volt batteries, and cell phone batteries. If everything is charged. There's too many electrons. I'm going to ask you this on the final exam. How many times am I saying this now? Okay, so let's pretend that the battery is fully charged. I think I can erase some things. Oops. All right, so we'll say the battery is fully charged, and we're not going to worry about this junk over here. We're just going to worry about the airplane stuff. So we turned on the electrical master switch. So now anything that's turned on can start working. And just so you know, the Hobbs meter, I didn't draw it in here, but the Hobbs meter on the airplane that's connected to the engine oil pressure, and that's how you pay for the airplane, it doesn't have an on-off switch. It's hooked up to the bus bar. Actually, it's hooked up straight to the battery, and it bypasses the bus bar. You can actually turn off the electrical master switch, and it'll still run. But, okay, so let's say this circuit breaker is working correctly, and we close this switch. And this is actually a bulb, a light bulb. If you want to call it a light, well, we'll call it a bulb. This is the electrical light bulb. If we close this switch right here, one side of the light bulb, it's already connected to the negative side of the battery. If we close the switch, that means that the positive side of the battery can go through the circuit breaker, through the switch, and through the light bulb. So the electrons can move. So when the electrons go through the inside of this light bulb, an energy conversion occurs. The electrical power turns into light. It also turns into heat because most light bulbs get hot. But this light bulb, just remember, this light bulb wouldn't work unless this switch was closed and the master switch was closed and the battery had electrical power. So generally speaking, in the airplane, we turn on the master switch and we start the engine and we turn on the alternator. So this switch right here is the alternator switch, and I'm going to abbreviate it ALT. In little tiny airplanes, there are two good sources of electrical power. You're going to write that down. One is the battery, and the other is the alternator. The problem with the battery is, if you don't charge it, it has a limited amount of electrical power. And it varies how long it'll last based on how much stuff you got turned on. If you've got all the radios on, you got the landing light turned on, you've got the position lights, you've got the strobe lights turned on, you got the intercom turned on. If you've got everything turned on in that little tiny two-seat airplane, that battery might only run for 20 minutes, maybe 30. It really varies. But if you've got the alternator working, you can run everything for a long, long, long period of time. So here's the way it works, and I know this is going to be a little confusing, so I'm going to end up saying it 3 times. When you turn on that alternator switch, now when you're driving a car, that alternator switch is hooked into the key. So it's not a separate switch. But on little airplanes, it's a separate switch. It's usually right next to the master switch. If we turn that on and the alternator is spinning, we'll say that the alternator, whoops, you know what? I made a mistake. I hope you'll forgive me. This is the alternator. And this one's going to end up being the ammeter. I'm sure you're taking your notes in pencil, or you'll just have to cross it out. So let's say that we've got in the airplane, we've turned on the master switch, we start the engine up, and we turn on the alternator switch. And we'll say that the alternator is spinning. That alternator, if everything's working right, it's going to produce electrical power. In your car, most cars are built on 12-volt systems. The difference between a 12-volt system and a 14-volt system is nothing. It's just what you call it, 12 volts or 14 volts. You don't have to write this down, but if you go out to a car, right? It's a brand new battery. It'll read about 12.6 volts, a little over 12 volts. But if you start the car up and the alternator is working, It will put out 13.5 or 14. This system might be called a 12-volt system or a 14-volt system, but in reality, it's no difference. Effectively, when the battery is on, when the alternator is on, about 12 volts, the alternator is going to have close to 14. So if somebody has a 12-volt system or 14-volt system, they're talking about the same thing. So we get this alternator up and running, and this alternator, this battery over here, if it's putting out 12.6 volts, the alternator is going to be putting out 13.5 to 14 volts. So it's a little bit higher voltage. And that's important to understand because in an electrical system, we're talking about an alternator or a generator. Power. Higher voltage. So what that means is when you turn on the engine and the alternator kicks in and it starts going, the battery doesn't discharge and power anything at all. The alternator provides all the power. In fact, we could even, if we wanted to, say that this is the negative side of the alternator and this is the positive side of the alternator. And all these other components over here, the electrons are going to leave the alternator and it's going to power the light bulb. And if we wanted to draw a picture, we could say here's the dotted lines where the electrons are going to go. And if this device was working, the electrons would go in this direction. And they would all the power would be produced by the alternator. Have I lost anybody yet? Okay, we're going to let this sink in and try it again tomorrow. So let's see, it is 10 and a half after in real life. So at 21 after in real life, please be back here.